Okay, yeah, so my name's Ben. I work at REA Group. Just before I get started, can I get a sense of who has ever done any programming with the F-monad in any language, in production or experimentally? So maybe about 5% of people. That's good. That justifies a bit of a pivot in my talk topic. So rather than getting work done with something, we're just going to look at the road to the F-monad. And that's really because I think you have to understand what something is before you can get work done with it. So a bit more of an introductory approach. But I want to begin the talk looking at monads and the effects that they carry. So let's start with the option monad. So if we have an option of A, this is Scala syntax. In Haskell, you'd pronounce that maybe of A. That holds either a value of type A or nothing. But I'm going to use a slightly different language. I'm going to describe that as being a computation that yields an A and additionally has an effect. And that effect is that the computation may have stopped. So if the computation stopped, we never get an A, so that's the empty case. If the computation's still running, then we get an A, and we can keep going. So we have a map operation on option, which you can see that function f from A to B, and that kind of says, if the computation's still running, then turn the A into a B. So we're chaining an extra stage onto our computation. We also have the flat map operation, which can turn a B into an option of C. So in the language of effects, this is saying perform a transformation in this computation, but additionally it gives you a chance to introduce an effect that wasn't already there. And we end up with an option of C. So there may have been an effect there, or we may have just introduced one. It's the job of a monad to join or to flatten those two effects down potentially and just give us a result that contains the effect that the computation may have stopped. Let's look at future in Scala. So approximately, a future represents a value that will be available at some time in the future. Another way you can describe it is kind of saying that the computation that's occurring inside the future is in a detached time, an asynchronous time that's not in the same time as outside the future. When we perform a map over a future, we're adding an additional processing stage or computation onto that value when it becomes available. It will run that. When we do a flat map over a future, we additionally get to introduce more asynchrony or more delay so that the computation of the C here can happen at a later time, a detached time, that's not the same as the time that it was triggered. So they're separated in time. All we know is that future C happened after future B. Let's look at the reader monad, perhaps a little bit less of a household name. So a reader monad takes an additional type parameter CO, which here I'm meaning by that configuration. So a reader monad essentially represents the idea of dependency injection. The idea that in order to do the computation, we have to provide some additional information at a later time that is necessary for that computation to go ahead. Once that computation gets that information, it will run and yield a value of A. If we map, we're saying once that computation runs, we get given our configuration, run it, and then perform an additional step to give us a reader of B, because we still have that dependency on that information being provided. When we do a flat map, we're also saying I'm going to yield a computation, I should say reader of COC, that itself depends on configuration being provided. And the monad takes care of, if you like, threading that configuration information into all the parts of the computation that need it. So it's really like very much the idea of dependency injection. Okay, so hopefully you get a sense looking at these three different monads that there's something common to them in the nature of a monad, that it represents some kind of chainable computation where the flat map and map operations allow us to chain computations together. But hopefully you also saw that there was something about each of those monads that was different and unique that separated them from the other two. And those are the effects of the monads. And so that idea there of there being some kind of effect living in every monad, except perhaps the ID monad, is something I want to delve into a little bit more. So here, if you are familiar with Scala, you may not recognise this syntax. I am using the kind projector plugin. My view is don't leave home without it. That allows you to write partially applied types in Scala more elegantly. So what are these effects? So when I first started learning about functional programming, the word effect to me was synonymous with side effect. I just thought that's what effects were. And then I can remember feeling quite perplexed when I read Applicative Programming with Effects, a really seminal paper from 2008 that was talking about these effects, and yet in the context of a pure program. And I was like, but what are the effects? This is a pure program, there are no effects. And it's not really explicitly called out, but there's effects consist of side effects. Hopefully you've got some notion of what they are. But there's also computational effects. And computational effects are transformations that are performed over a pure program that turn it into another pure program, but nonetheless are pure. And in almost all cases, you see them modelled as a higher kind of type. So a type that takes another type as a parameter. And the type inside is the value that's yielded, and the type on the outside that does the wrapping represents the effect that is present around that value. The examples we've seen so far form into this category. Okay, so you quickly run into the problem when you scale up software of needing to put things together. So if we've got some effects that we want in our program, how do we combine multiple effects together? So one of the early popular ways of doing that was stacking effects in monad transformer stacks. So in this example we can see here, we want two effects. We want to be able to inject some configuration at a later stage into our computation, but we also want a computation that may stop. So we can create a monad transformer stack that includes both of those types. That stack is ordered, so there's an alternate stack we could create that puts the two monads in a different order. And they're different types and have similar but different meanings. If we were to now combine future with that, we would then end up with a triple stack that now has the effects of delaying the computation, requiring configuration, and potentially stopping. The problem is that there are lots of different orderings of that. Not all of them are legal, but in general, if we have n different monad effects we want to combine, we get n factorial different possible orderings of that. That can be a problem in practice because even if me and my coworker are both working with the same effects, if we use different orderings of those effects, then we can find our software has different types in it that aren't compatible. We need extra boilerplate to put those two modules together. Another problem you encounter working with monad transformer stacks is when you didn't want all the effects that are present in your stack. So if your overall computation needs 3 effects present, but you have pieces of your system that work in less with fewer effects, you end up needing to do lifting or wrapping to express your whole computation in some uniform type that everything can work in, and that can result in extra boilerplate. Okay, I want to change direction slightly and just look at the interpreter pattern in Freer Monads. So this is an idea that's been around for many years and really lies at the heart of functional programming, which is the idea that a purely functional program should compute a description of what to do and not simply do it. And then it should feed that description into an interpreter that does it and acts upon the world. And for me, one of the most tangible wins of this, and really the most tangible win of functional programming in general, is that it's very easy to verify the correctness of that description if you haven't actually got side effects going on, and you've just got the description there. So the Freer Monad serves as a language to express that description of what to do. And it yields a value A, and it's parameterized on this type E. And E can represent a family of functors. A functor is roughly a container, but you can also view it as a family of effects or a domain-specific language to describe what can occur in that program. An example of that taken from the CATS website is a free of a KV or key value store that finally yields an A. But the key value store family of functors consists of functors that encapsulate operations on a key value store. Getting a value out of the store and yielding a read of a value A from the store, putting into the store and deleting a key from the store. And the Freer Monad lets you chain together a computation consisting of those operations. Again, if we think, well, how do we scale up? How do we put our program together with another program? If I had another program where I wanted to read configuration, how can I combine these two programs together? The most successful technique has been to use a growable type, this co-product type, represented by the colon plus colon here. And what that type basically says is we have a free monad whose operations are, or whose effects are either key value store effects or read config effects. And that's a type that consists of this type or that type. And we can grow that type further to add as many different operations into our DSL as we wish. So finally, these ideas kind of are really what form the basis of the F monad, but the F monad takes the free monad and kind of specializes it or focuses on a very, very focused idea of effects being in the DSL. So, the Eff-cats library is one of a pair of libraries. There's also an F-Scala Z library, because cats and Scala Z are kind of the two foundational libraries available for functional programming in Scala. It's written by Eric Torreborre, who is formerly of Sydney, and he's been down to Melbourne before. He's now moved to Berlin. He also wrote Specs2, the Scala testing library, and he has great attention to detail and tends to write very correct software, which is one of the reasons why I first got interested in F. It's got good documentation and it's all open source on GitHub. So this is the core abstraction in the F library. An F, which is kind of a type of free monad, which takes two types. An F represents a computation that will eventually yield you some type A. Along the way, it's going to have to resolve some computational effects or some side effects in the process of yielding that A, and that is described by a type-level set of effects, R. So let's look at an example of what an F method looks like. So this method, update name, we'll come back to the things in the type brackets first. It takes two parameters, a name and a person, and its job is to compute a person with an updated name, resolving the effects along the way. And the effects that are present are described in the type by this type-level effect stack R. And what those guys there represent is the effects that this method requires to be present in the stack. There can be others, but at least these three. There must be an error effect. An error effect says that this type can fail. This computation, rather, can fail with an error message. XOR is the cat's equivalent of disjunction, which we saw in Sharon's talk this morning. It's got dependency injection. It's got the reader monad present. So this method requires some configuration to be injected later. And it also needs to do some logging. So it's got a logging effect present, which is a writer monad of string, which means it can emit some additional information as a side effect of the computation. Another way we can write this, and the way I'd probably write it, is also to actually factor out the passing in of a person, updating them, and then passing it out into a state monad. So a state monad indicating that we're updating the state of a person, as we call this method, and now the return type is unit. There'll be a unit or no value returned in the F. It's all now done through the effects. So that's what this method could look like inside. So here we've got a bunch of operations inside a for expression. In Haskell, this would be a do expression. So these operations are sequenced together using map and flat map. So this is a monadic expression. Let's look at some of what we get. So by virtue of these effect type class, member type classes being there, various syntax is enabled. So we get an ask method that lets us read the configuration. We get left and right that let us signal there's been an error in the case that the names exceeds the maximum length in the configuration, or we can indicate that all's well by passing the next value out through a write. We get the ability to read from the state monad with that get syntax there, and we get the ability to put back into the state monad with the put syntax down the bottom. And finally, we get the ability to do logging from the log effect that's present using the tell operator. Okay, so again, that's how we can create one piece, one fragment of a pure effectful computation using F. But how do we put them together? So there's our update name method again, and I've highlighted the 4 effects that we've indicated must be present in the effect set to call that method. Here's a second method that's got some overlap and some different effects that have to be present. The random name method generates a random name and gives it back to you as a string. And that needs a random number generator seed passed in as a state of RNG. It also reads the configuration and it also does some logging. So 2 of those effects are present in the first stack and 1 of them is not. If we want to write a method that combines these 2 fragments of the program together into a larger piece, we can do that. And what we have to ensure is that the effects present at the top level are the union of all the effects present in the pieces of the computation. So here we can see all 5 effects need to be acknowledged as member type classes in the signature there. And again, we compose, F is a monad, so to compose it, we use a monadic for expression there. So first we call random name, getting out a name, and then we call update name. I think there's a slight error because it actually takes a name wrapped up in a type, not a string, but the essential idea is as illustrated there. Okay, so we've seen, in a way, how you work with effects and how you create effects and use them in your code. But at the end of the day, the effects have to get interpreted to yield our final value. Let's look at that. So, as we said earlier, an F yielding an A will give you that A only once you've acknowledged all the effects and resolved them, because they have to have a chance to transform the program. So we'll start with an update name. And the first effect we're going to resolve is the reader effect by giving it the configuration that it wants. So we'll create a configuration with some defaults, and we'll use the runReader method, which will be available if your program computation has a reader effect. And the result of that will be a new set of a new effect stack S that's had the reader effect removed now, because we've dealt with that, we've given the configuration. So S is a smaller set. We can do that again to resolve a state effect. Now a state effect takes an input state and returns a final state. So in this case, we're going to do that for person. We pass in an example person object here. The state gets updated, and what pops out now is a tuple of the original unit that the F yields plus the updated state. Let's keep going. Yep, saw that. That's the same thing. So it's just reproducing the last line. The next effect we're going to run is the possibility of error. So runZOR will now consume the error effect, and on the output side, we'll now get a string being the error message, or XOR, exclusive or the updated state of the person. We've only got 1 effect left. We'll run that effect, and writer, so that's going to emit an additional log. So the result now of our computation is going to have a failable value plus potentially some logging. And now we've got a null set of effects left. So there's no more effects left to metabolize. So we can go ahead and run that program. And it's only here when we run it that the actual program runs. This is the point where the code literally executes, and if you had side effects in there, would occur. Okay. Thank you. So for each type of effect, you need a handler which knows how to resolve that effect and remove it from the stack. It's a bit tricky to write them. I have actually really just used the pre-existing ones. There's quite a vocabulary provided with the library. Validate handles errors but accumulates failure messages. List and choose effects allow you to kind of generate multiple different alternative options for your computation. Sometimes called non-determinism or branching. Error is another kind of XOR that also traps exceptions, and eval gives you laziness. Effect interpretation is very flexible. You can interpret them in any order you wish. You can interpret them inside your pure program. You don't have to interpret them just at the boundary. You can use a non-pure interpreter that has side effects during interpretation. For example, a DB action effect could read and write to a database. And for effects that are task or future style that do something, you can interpret them either in parallel, which runs all the futures in parallel, so-called applicative interpretation, or monadic, which will run them all sequentially. And you can make that choice at the time you execute. And finally, these are kind of power techniques that you find yourself using when you really use this in anger. Effect translation lets you turn a stack of effects into a different stack. So, for example, we could weaken the state effect to a reader of person if we had a piece of code that didn't need to update the state of a person just to read that state. Or we could strengthen the state of a person to a DB action if we wanted to interpret that and cause side effects. For effects that have a second type, which is kind of their focal type, you can use functional lenses. You can compose lenses with effects to lens the effect. So where you've got an effect that updates a person, you can use a lens between between person and address to transform that effect into a state of address. And that's all I have for you. Well, not quite, because we've got the unconference tomorrow. So if you want to try F out for yourself, come and find me and try this stuff out in practice. Thank you.
All right, that was excellent, Ben. And awesome that you'll be at the unconference as well to do more hacking. So any questions for Ben? Oh yeah, we've got two up the front.
Hello. As far as I understand, there are some different problems that occur with extensible effects. For example, some of these effects, sort of, you cannot actually reorder them in this way and handle them however order you want. For instance, the continuation passing monad and writer, if you do them in the wrong order, you break the writer laws. And different extensible effects frameworks sort of get around these problems in different ways. So I'm curious, how does the CATS F thing deal with these kinds of problems?
Yeah, so I've hit it once where I had effects in some order and I was trying to resolve them in an order that was illegal. It shows up as a missing implicit in Scala, so it shows up as a compile error, but it's not, admittedly, it's not very easy to interpret the meaning of the error as indicating that you've tried a combination that's illegal. And in fact, I had to get Eric's help or advice to figure out what was going on. Having said that, it hasn't been a common problem for me in practice. It's occurred once in several months of programming with this.
Cool, thanks.
My question is basically the same. Yeah, Ben, I have a question for you, actually. So I think reading ages ago on the Haskell mailing list, someone was talking about how they often found they got better results from writing a specific custom monad for their given task. And he said they'd tried a few other things, but that's what had worked well in, I think it was GHC. So obviously you've had experience working with the F monad now and also probably writing many other custom monads. So could you just compare and contrast those two approaches a little bit and what you liked, what you didn't like?
We haven't used F yet at REA in production. Being a large team environment, we kind of have to socialise new techniques for quite a while and let them gestate before we can apply them. We have used free monad-based DSLs and we have used monad transformers. I think we're having a pretty good time with free monad-based DSLs. This is probably a refinement on that. Monad transformers we didn't have a great time with. We did find a little bit of brittleness there for the reasons I described earlier.
Excellent, thank you very much. Well, let's thank Ben one more time.